Hi guys! So in this discussion, we will be working on some examples of series where we use comparison tests to determine whether the series is convergent or divergent. So let us recall what we have so far. First, the definition of the convergence or divergence of a series. So the series sum from n equals 1 to plus infinity of an converges if its sequence of partial sums s sub k is convergent. Otherwise, if this sequence of partial sums is divergent, then this series here is also divergent. So let me recall what s sub k is. Your S sub k, this is the sum of the first k terms of the series. So a sub 1 plus a sub 2 plus you continue plus until you have a sub k. So partial sums. Okay? Then we recall what we call the divergence test. Okay? So if the limit of the terms a sub n as n approaches infinity is not equal to 0, then the series a sub n is divergent. So take note that this statement here is a test for divergence. This is not a test for convergence. So do not use this statement in order to prove the convergence of a series. That is a mortal sin. Okay? Next, let us recall the integral test. So let the series an be a series of non-negative terms. And suppose we have a function f that is continuous, okay, on the interval probably from 1 to plus infinity, okay. The function f is positive, meaning it is the f of x is greater than 0 for all x greater than or equal to 1. The function f is also decreasing on the interval 1 to plus infinity. And finally, if we evaluate f at every positive integer n, so f of n, that is equal to a sub n. Okay? Then, our conclusion is, this series converges if the improper integral from 1 to plus infinity of f of x dx converges. Okay? And this series diverges if the improper integral from 1 to plus infinity of f of x dx diverges. Okay? Now, this condition here, okay, this condition here can be modified into the following. So uh, we can say that we need the function f to be positive, okay, for all x greater than or equal to k for some positive integer k, okay, for some positive integer k, integer k. And therefore, we can also change the interval here where the function is decreasing. So we can put this, instead of the interval 1 to plus infinity, we can replace this to the interval k to plus infinity. And with this modification, we change now the lower limit of integration of the improper integral. So instead of 1, we can just replace this with k, also this guy here with k. And the conclusion remains the same. Okay? So the reason we can change this condition here is that, take note that this series here, we can rewrite this into, or we can decompose the series into sum of a sub n and from 1 up to k minus 1, okay, plus sum a sub n and from k to plus infinity. And take note that this is just a finite sum. Okay? So this finite sum won't affect the convergence or divergence of this infinite sum in here. Okay? So whatever the convergence or divergence of this series, it will follow that this series have the same conclusion or has the same conclusion as this series here. Okay? So, let us recall the next test. Okay? We have the comparison test. So, let us consider a series with an as terms and another series with bn as the terms such that an and bn are non-negative. Okay? Now, if an is less than or equal to bn for all n, and the series bn is convergent, then the series an is also convergent. However, if an is greater than or equal to bn for all n, and the series bn is divergent, then the series an is also divergent. Okay? So, you can think of this guy here, these conditions here, or this statement here as follows. If something is bigger, okay, if something is bigger and that bigger is convergent, then everything that is smaller than that will also be convergent. Okay? So, however, this statement here, if something is smaller, is already divergent. Okay? If something is smaller, is already divergent, then everything bigger than that smaller something will also be divergent. Okay? So, in here, to use comparison tests, it is important to know certain convergent or divergent series for comparisons. Okay? For example, the geometric series or the piece series, or you have some telescoping sum, etc. So you can use those series for comparison. Okay? So, let us work on some examples. First one. So, determine whether the series is convergent or divergent. So, notice this guy here. We have the series 1 over n cubed plus 8. Okay? So, notice that in here, an obvious series that we can use for comparison is the series 1 over n cubed. Okay? And I say obvious because it's the one that you will see immediately in here. Okay? So, note that your n cube, this is less than n cube plus 8, which means that in here you have 1 over n cube plus 8. This will be less than 1 over n cube. And of course, here we are saying this for n greater than or equal to 1. Okay? And therefore, if we consider this series 1 over n cube, okay, which is greater or at 1 over n cube is greater than 1 over n cube plus 8, and if we show that the series 1 over n cube is convergent, then we conclude the series 1 over n cube plus 8 is also convergent. But indeed, the series here 1 over n cube and from 1 up to plus infinity, this one is convergent since it is a P series. Okay? So P series with P series with P equals 3, and this is greater than 1. Okay? So we conclude immediately that the series sum 1 over n cubed plus 8 and from 1 up to plus infinity is also convergent. And that is because of the comparison test. Okay? Next, here we have the sum 9 to the n over 3 plus 10 to the n, okay? Where n runs from 1 up to plus infinity. So if we look at this, an obvious series that we can use is the one which involves these two guys here. Okay. So this is what we know. Um, your 10 to the n, this is less than 3 plus 10 to the n, which means you will have 1 over 3 plus 10 to the n will be less than 1 over 10 to the n. And of course, if we multiply both sides of the inequality here by 9 to the n, and since 9 to the n is positive, the inequality won't change. Okay? So in here we have 9 to the n over 3 plus 10 to the n. This will still be less than 9 to the n over 10 to the n. And this is can be written, or this can be written as 9 over 10 quantity to the n. Okay? Which means we can use the series with these terms, okay? With these terms for comparison. Okay? But notice that here you have 9 over 10 to the n, and from 1 to plus infinity, 1 to plus infinity, this one is convergent. Okay? This one is convergent because it is a geometric series, okay, with R, the common ratio. So, geometric series with R equals 9 over 10. Or in absolute value, this guy here, it's less than 1. Okay? And therefore, by comparison test, the series 9 to the n over 3 plus 10 to the n, and from 1 up to plus infinity, this one is also convergent. Okay? Let's look at our next example. So, we want to determine whether the series sum from n equals 1 to plus infinity of ln of n over n is convergent or divergent. Now, an obvious series that we can use to compare this with is the harmonic series, or the sum 1 over n. Okay? But before we use that, let us expand this a little. So in here, this series here can be written as ln of 1 over n, or over 1, plus ln of 2 over 2, plus starting from n equals 3, we write the infinite series. So sum from n equals 3 to plus infinity of ln of n over n. Okay? So why do I need to rewrite this series into this form? Well, first, here we have ln of 1, and that's equal to 0. So basically, we can actually start from n equals 2. Okay? This ln of 2, however, this is less than, or this is less than 1. Okay? Whereas, starting from n equals 3, this ln of n, this is greater than 1. Okay? So, with that, for n greater than or equal to 3, we have 1 less than ln of n. Okay? And therefore, if we divide both sides of the inequality by n, okay, this means that we have 1 over n less than ln of n over n. And we need this, okay? We need this because we know that the series 1 over n and from 1 up to plus infinity, or let us start with 3 here. So the series from n equals 3 to plus infinity of 1 over n, this is divergent. It is a p-series with p equals 1, or we know that this is the harmonic series. Okay? And therefore, since we have this inequality here, it follows that the series sum ln n over n from 1 or from 3 to plus infinity, this guy here is also divergent. And of course, if you add this ln of 2 over 2, okay? If you add ln of 2 over 2 to this sum, this is still divergent. And therefore, this original series here is divergent. Okay? For the next problem, we want to determine whether the series from n equals 1 to plus infinity of 1 plus cosine n over e to the n is convergent or divergent. Now, for this, an obvious series that we can use is the series which involves this guy here. Okay? So we will try to compare this series with the series 1 over e to the n. Okay? Before we do that, first, let us have the following analysis. We know that cosine of n, this is less than or equal to 1, but greater than or equal to negative 1. But we will not need this, or we will not use this guy here. What we need is that cosine of n is always less than or equal to 1. Okay? Which means that 1 plus cosine n, this will be less than or equal to 2. And therefore, we have 1 plus cosine of n divided by e to the n. This is less than or equal to 2 over e to the n. And therefore, we will compare this series here with the series with terms 2 over e to the n. And then we can just factor out that 2, and therefore, we can actually compare this with 2 times the series 1 over e to the n. Okay? But we know the series 2 over e to the n, and from 1 up to infinity. Let's just rewrite this as 2 times the series, and from 1 up to plus infinity of 1 over e to the n. We know that this is convergent because it is a geometric series, okay, with r 1 over e, and 1 over e is less than 1. Okay, so this is a geometric series with absolute value of r, which is equal to 1 over e, and this is less than 1. Okay? So, if something bigger is convergent, then that smaller guy will also be convergent. Okay? So, we have the series 1 plus cosine n over e to the n, and from 1 up to plus infinity is also convergent. And again, by comparison test. Okay? For our next example here, we want to determine whether the series sum from n equals 2 to plus infinity of square root of 1 plus n over n minus 1, okay, is convergent or divergent. Okay? Now, look at this. This is a radical expression, and the one inside the radical sign, it's a polynomial. Okay? And then the denominator, it's a polynomial. So here's a tip. You can compare this expression here or this term here with the highest degree that you see in the numerator divided by the highest degree that you see on the denominator. Okay? So what I mean there is you can consider the term square root of n over n. Okay? Square root of n over n, or this is just 1 over square root of n. And try to use this term, try to compare this term with this term here. Okay, so if we consider the series with this term, this is a p series with p equals 1/2, and that's less than 1. And therefore, the series with this term will be divergent. So, with that, try to make sure that 1 over square root of n is less than or equal to these terms here. Okay? But that is easy. Okay? That is easy. Because, let's look at this. Okay? Let's look at this. We know that square root of n, this is less than square root of 1 plus n. Okay? We also know that n, okay, it's greater than n minus 1. And this inequality here tells us that 1 over n will be less than 1 over n minus 1. So, this left side in this inequality, I multiply to the left side of this inequality here. And the right side of this inequality here, I'll multiply it to the right side of this inequality here. And the inequality won't change, meaning we still use this less than. Okay? Meaning, what we will get is that square root of n over n will be less than square root of 1 plus n over n minus 1. And of course, this is true for all n greater than or equal to 2. Okay? So, we now have that square root of n over n, or 1 over square root of n, it's less than this guy. And we know that this 1 over square root of n from 2 to plus infinity, or we have here 1 over n raised to 0.5, n from 1 to plus infinity, or n from 2 to plus infinity. This is divergent. Okay? This is divergent because this is a p series with p equals 1/2, and this is less than 1. Okay? And therefore, this guy here is also divergent. So, we have the series. Okay? We have the series square root of 1 plus n over n minus 1, and from 2 to plus infinity, this guy here is also divergent. Okay? For my last example, let's have some proving here. So, prove that if a sub n is greater than or equal to 0 and the sum a n converges, then the sum an squared also converges. Okay? So, we will use comparison test in order to prove that this series here is convergent. So, how are we going to use that one? Of course, we assume that limit of a or that the terms an is are greater than or equal to 0. Okay? Now, since the sum an converges, okay? Since the sum an converges, the limit of an as n approaches plus infinity, this must be equal to 0. Correct? This is the theorem where we obtained the divergence test. Okay? Now, if the limit of an as n approaches infinity is equal to 0, okay? At some point, okay, starting from some positive integer k, okay, the terms will be less than 1/2. Actually, what we need is just that the terms will be less than 1. Okay? So, for some positive integer k, okay, a sub n will be less than 1 for all n greater than or equal to k. Okay? If you don't believe that, let us try to sketch that. So you have this, okay? You have this. Your limit an as n approaches plus infinity, it's equal to 0. So if this is 1, then at some point, maybe your terms are like this. You have something like this, something like this. Okay? Okay? Those are your terms. But in the end, since the limit is equal to 0, okay, the terms must go down and down and down and down there. Because your limit is equal to 0. And all of those terms will be less than 1. So this probably here it's our k. So for some positive integer k, an will be less than 1. Okay, for all n greater than or equal to k. But what does this mean? If your number is less than 1, okay, the square will be less than the original number. Okay? If your number an is less than 1, then the square an is also less than, or the square an is less than an. Okay? So, we have here an squared will be less than an. And this is true for all n greater than or equal to k. Just think of it. You have 1/2, that's less than 1. If you square it, that's 1/4. And 1/4 is less than 1/2. Okay? If you have 0.9, okay, 0.9, that's less than 1. If you square it, that's 0.81. And 0.81, it's less than 0.9. Okay? So if you have a number that is less than 1, if you square it, that square will be less than the original number. So what? Again, series an is convergent. Therefore, the smaller guys will also be convergent. So, since the sum an again is convergent, okay, the sum an squared, and from k to plus infinity is also convergent. And therefore, the entire series will be convergent. So, the series a sub n squared is convergent. Okay? And that's again by comparison test. Okay? So let's put the comparison test reason in here. By comparison test. Okay? So, that's it from me for this discussion, and thank you for listening, and I hope you learned some techniques in this or from this discussion. So, thank you and bye-bye.